Hey guys, welcome to the second set of notes. Today we're going to talk about uncertainty and errors. Notes themselves a little bit longer. Hopefully I will be a little bit more succinct and it won't be quite as long. And we're going to address uncertainty and error. And first we'll start by talking about the different types of errors. So there are two main types of errors that we're going to encounter this year. Really, all types of errors can be one of these two. The first is what we call random. And these are mistakes on the part of the individual. These are the things that in previous classes you've probably recorded as human error, and hopefully your science teachers have put a big red X through and said, human error is not something you put in a lab report. You are specific. You say what actually happened. Misreading the scale. And actually, see this, I don't even like this. Because that's not an error, that's just a mistake, right? That shouldn't be, that's not a source of error. When we write lab reports, we shouldn't be writing out, I miscalculated, right? That's not an error, that's a mistake. Better examples of random error are, you're doing a lab on free fall, and all of a sudden there's a gust of wind because you're doing it outside that blows your object off course. That's a great random error. It happens once or twice. It doesn't affect the entire data set. When you have small random errors, those types of measurements, those types of readings or data sets are said to be precise. And that means the data is all going to be around a reasonable, within a reasonable range of the other pieces of data. Systematic errors are ones that affect your entire data set. It's your balance is miscalibrated. Your balance that you're using happens to be off by 0.3 grams. And so what that means then is that your entire set of data is going to be off by 0.3 grams. And so you might have precise data. It might be all very, very close, but it's all going to be offset from the actual value by 0.3 grams. When we have small systematic errors, these are measurements that are said to be accurate. So our biggest difference between the two: random errors only affect one or two data points. Systematic errors affect the entire set of data. And we have to take these things into account when we're doing experiments, when we're making measurements and doing research, because the amount of error affects our precision and our accuracy. The precision is how close all of your values are. Did you measure the mass of a ball 5 times, and you measured it once and it was 5 grams, and you measured it a second time and you got 48 grams, and this third time you got 12 grams, and then you got 30 grams, and then you got 1 gram. Right? Those are not very precise. Those numbers are widely scattered over a very large range. And so when you look at something like that, when you have data that's should always be the same or near the same, and the data points are all over the place, you need to realize that there must be some type of random error impacting your data because of the lack of precision, and that's when you go back and review your method and see what happened. But when you have a very precise set of data, that tells you have a low random error, which is a good thing. And then accuracy is more the how close are you what it actually should be. If it's something that we're trying to find that we're comparing to an accepted value, how close is it to the accepted value? The greater your accuracy, the lower your percent error is going to be. And accuracy is impacted by that systematic error. Do you have something that is affecting your entire data set that's skewing all of your data by some factor? And so the most common, the most widely used Example of this is a target for arrows. And so if we look at these, we see this guy right here that's circled in green. Here we have all over the place, right? You got one up here and one down here and one over here. So none of these are near each other. You do have one, we got one that we got a lucky shot, right in the middle, or near the middle. All over the place. Low precision because they're not together. Low accuracy because they're not where they're supposed to be. If we go to the right here and we look at this guy, the low accuracy, high precision. So here we have this nice cluster of data points, of shots. They're all really tight. Okay, so here maybe there was a steady left breeze that blew all of the arrows the same amount for every shot, and so it affected every single shot almost the exact same, but they're all very tightly clumped together, so they're very close together, but they're not accurate, right? We're not in the middle where we should be. So low precision, high accuracy. High accuracy, low precision. Here you can see that the shots are all within a reasonable distance of the center of the target, of where you're trying to get to. But there's a pretty good range of separation between those shots. And so there we have high accuracy but low precision. And then what our goal should be, what we should be looking for in all of our data, all of our lab work, all of our research, is this final one. This is what we're trying to achieve. High accuracy, high precision. Our data is what it should be. There's low systematic, low random error. That's a good data set. This is what we want every single time. The next piece of this then has to do with the uncertainty in our measurements. And the uncertainty, when we talk about uncertainty, really it's dependent on the device, on the measuring instrument that we're using. It tells us how accurate we actually can be, because for instance, if I have a meter stick, but that meter stick only has a 0 and a 1 meter graduation, so it's something like this, and 1 meter graduation, and the thing that I'm measuring is somewhere in this realm, the best I can do is estimate. And so I'm going to look at my meter stick and I'm going to say, well, it's here, and that's about 80% of the way. And so I'm going to call that 0.8 meters. But ultimately there's a pretty high level of uncertainty in that measurement because there's so much estimation. If, on the other hand, I have an actual meter stick, which has graduations down to the millimeter, those are millimeters, then I can get a much more precise reading, because then I can zoom in and say, oh, well, that's clearly right between the 789th millimeter and the 790th millimeter. And so the actual measurement then must be 789.5 millimeters. But that all depends on the device that we're using and what the detail is of that device. What is the ability of that device to measure with greater and greater levels of precision. Now, ultimately, when we see that as more decimal places, and the greater the decimal place, the greater the level of precision and potential accuracy that we could have with the measurement. This is going to come into play with our two different types of devices. We have two different types of measuring devices that we're going to be using this year. First is analog. These are our meter sticks, our triple beam balances, things that don't have a digital display, things that have a needle that gets deflected, or that we have to observe and look at where does it fall between a group of numbers. And with our analog devices, such as our meter stick that we have pictured here, the level of uncertainty is always going to be half of the smallest graduation. So in this case, our graduations are millimeters, right? And if we zoom in, our big numbers here, so our 97, our 98, our 99, these are centimeters. Ooh, that's a highlighter. There's centimeters, which makes these guys here and here and here and here and here millimeters, or tenths of centimeters. So 97.1, 0.2, 0.3, et cetera, et cetera. And so what that means is that the smallest graduation of our meter stick is a millimeter. And so our uncertainty then is going to be plus or minus, and this is how we're going to write this, 0.05 centimeters in this case, or we can say plus or minus 0.5 millimeters, depending on what units we're actually using for our measurement. And so the way that we would see this then, what does this all ultimately mean? Let's say I have some object that I'm measuring, a stick or whatever it happens to be, and we see here that it falls on our meter stick right about here. And so I'm going to make a measurement of this object, and I'm going to say, well, 98.1, 0.2, 0.3. So it's 98.3, but clearly it doesn't fall right on the 0.3. It's somewhere between 0.3 and 0.4, and we need to reflect that. We can't just round our measurements. As scientists, as investigators, we want to be as accurate as possible. We want to have as precise, accurate results as possible in all of our research that we're doing. And so it's not enough to say 98.3, 98.4, whatever. We want to estimate that first uncertain digit, and we should be doing this in all of our readings using analog devices. And so in this case, I'm going to say it's about halfway between the 3 and the 4. So what that would then make our measurement is 98.35 centimeters with an uncertainty of plus or minus. Actually, you know what? We're going to hold off on this part. With an uncertainty of plus or minus 0.05, and we can just put the units at the very end. And so what this means, what does this tell us? What it tells us is that our measurement is to a very, very high degree of certainty, somewhere between 98.30 and 98.40 centimeters. Now, what you should see then is that if we have smaller and smaller graduations, if we had down to fractions of millimeters or things like that, if we were able to say that it was 98.3345 plus or minus 0.0005, then we have a much better level of accuracy, of precision in our measurements for that particular measurement. And so the more precise our instruments, the more precise our measurements, the lower or the smaller our amount of uncertainty is with our measurements. Now, one thing to note really quickly is that the decimal place of our uncertainty and the decimal place of our measurement are the same, and they always should be. You shouldn't have an uncertainty or a measurement that has a different number of decimals than your uncertainty. Those two should always match. They really have to. Now, if we have a digital scale, something like this, a balance would be the most common one that we use, multimeters, things like that. We can't estimate that first uncertain digit, right? It's not possible. There's no way to do that. So with our digital balances, it is plus or minus the smallest decimal, okay? And so for this case, our 125.30 grams is going to be then plus or minus 0.01 grams. And so that means that with a very high level of certainty, we can say that the mass of our pennies is somewhere between 125.29 and 125.31 grams. Okay. Now, once we have these, we'll write them as we just saw in that fashion that we just showed you. 33.5 plus or minus 0.5 is another example of this. This is what we call the absolute uncertainty. This is the uncertainty that we get from the measuring device. It has a magnitude in a unit. We write it just like you see here and just like we did in the previous slide. And again, when we write the absolute uncertainties, the decimal place of the uncertainty and of the measurement always need to match. Then we have fractional and percent uncertainties, and these are going to be important because sometimes percent uncertainty is just a more appropriate measure, but when we start carrying uncertainty through our calculations, then we're going to have to be using these as well. The fractional, we're going to divide the uncertainty by the actual measured value. What this is going to look like, and you'll often see when we talk about fractional uncertainty that it's kind of a delta. We'll see that on the next slide, but for the previous 33.5 plus or minus 0.5 meters, our fractional uncertainty would be 0.5 over 35.5. We would actually divide that out, and that numerical value, that value that we get would be the fractional uncertainty. Now, to get the percent uncertainty, and this is not percent error. This is a different measurement than percent error. We're going to measure the fractional uncertainty by 100. Okay, so those are two different ways we can express this. Quick example, and something to note here. If you're given a range of numbers or a data set and you don't have the actual measurement tool, the next best way to find the uncertainty is to figure out what half of the range is. And so in this case, our largest number is 2.8, our smallest number is 2.5, and so our range is going to be 0.3. Now, half of that is 0.15, but what you should notice is that the decimal place for our measurements is the tenths place. So what that means is that our uncertainty also has to be to the tenths place. So we're going to round that up, and our uncertainty is actually going to be 0.2. So our absolute uncertainty is plus or minus 0.2 newtons. We're going to take the average of our data set, which ends up being 2.63, but again, we have to round that to 2.6 because our average can't be more precise than our measurements. That's not possible. So our absolute uncertainty then in this case is 2.6 plus or minus 0.2 newtons. That's this right here. The fractional uncertainty would be 0.2 divided by 2.6, which is 0.077. And then the percent uncertainty is going to be 0.077 times 100, or 7.7%. Now again, our percent uncertainty, you'll notice, is to one decimal, just like our previous values. And so that's how we would calculate those two particular measurements. This, again, as I said, becomes important when we get into what's called propagation of uncertainty. And that means carrying our uncertainty through calculations, because throughout the entire year, we're going to be making measurements, but then we're going to be using those measurements to calculate other values and to draw other relationships. And when we make those calculations, we have to take in the uncertainty of the original measurements. It doesn't just disappear when we start multiplying, dividing, adding, or subtracting. So, rules for propagation of uncertainty. If we're adding or subtracting values, we add the absolute uncertainty. Now notice that it's adding or subtracting. The reason for this is anytime we bring multiple numbers with uncertainty in together, the uncertainty of the final value is always going to increase because both of those original values have some uncertainty. So even if we're subtracting the two values, we have to add the uncertainties together. Okay? If we're multiplying or dividing, we add the fractional uncertainty. And then if we're raising something to a power, we multiply the fractional uncertainty by the power. Which, if you're multiplying, it's just a specific example of this. It's just an easier way to do it. If we look at these in mathematical notation, and you're going to have ample opportunity to practice this, and we'll go through some of these in class, but please make sure if there are portions of this that you're not clear on, that you're writing down questions so that you can come in next class or before school and you can ask me about them. Okay, so here our first case, if our final value we're calculating y is equal to a plus or minus b, then our fractional uncertainty, which is delta y, is equal to delta a, which is the absolute, the delta y is the absolute uncertainty, then the absolute uncertainty delta a, which is the absolute uncertainty in this value, plus the absolute uncertainty in b. Okay, so that's for plus or minus. If our calculated value is equal to, say, a times b divided by c, then what we have here, this is our fractional uncertainty, right? The absolute divided by the actual is equal to the absolute in a divided by a, the absolute in b divided by b, the absolute in c divided by c. This is just the fractional uncertainty in each of the specific measurements, which gives us the fractional uncertainty in our answer, right? So this whole thing is giving us the fractional uncertainty. If we want to find the absolute, we then have to multiply this entire thing by our actual measurement to give us the absolute uncertainty. And then if y is equal to a to the power of n, then our fractional uncertainty here is equal to n times the fractional uncertainty in a. Again, it's a lot. It makes a little more sense when we start calculating, but questions are good. If you have them, please ask. And algebra is great, and algebra is awesome, and we're going to use it a lot, but we also have to show our relationships graphically. Okay, we have to be able to put these relationships in more than one form. Graphing is one of those, and again, just because we're graphing doesn't mean that we get to ignore the errors and the uncertainties. And visually, graphically, we represent our uncertainties using what are called error bars. And you've probably seen them. You have your data point, you have a line, a little line here, a line here. It looks something like that. This segment right here represents that uncertainty. This is the plus, this is the minus. And so if it's 40 plus or minus 0.5, then I guess it would have to be 40.0 plus or minus 0.5. This would represent 0.5. This would represent 0.5 on the graph. Okay, so that's how we recognize those uncertainties. And this area in here is what's called the zone of uncertainty. Okay, that's the range of possible quantities. And sometimes we'll have x and y values, so it might look like that. And then you have this zone kind of like that. Part of determining our relationships then is also not just plotting the data, but determining a fit line. And let's be clear, when we're talking about fit lines, particularly as IB defines it, a fit line is not necessarily straight. A linear fit or a direct relationship might have a straight fit line, but as they ask you to apply fit lines to data sets on IB exams and things like that, that line might be curved. Okay? And here we have an actual example of some data plotted. And you'll see that you have the error bars on each data point, and we know exactly what the amount of those error bars is because here in our label, and we're always going to label our x and y axes, it tells us that the uncertainty is plus or minus 0.3. So we have 0.3 up here, 0.3 here, 0.3 here, 0.3 here. So the absolute uncertainty for all of these data points is exactly the same. Okay, now we draw our fit line, and what you'll notice is that the fit line is this reasonable line that roughly goes through the center of all the data points. And the benefit, the upside of data points or of error bars on our data points is that, let's say I have an extra data point that's up here, and I put my uncertainties, my error bars, there we go, it's like that. Notice how the line of fit does not go through that zone of uncertainty. It can't, right? It doesn't make sense for it to. That is a great indicator that this point right here is what we call an outlier. Okay? And an outlier is one in which there has been a significant random error and the data point's not valid. And if you try and use that data point in your analysis, it's going to completely skew your analysis. And so if you have an outlier, we do not take it into our analysis. Now, that doesn't mean that we don't plot it. That doesn't mean we don't address the fact that there is an outlier. But when we do our final mathematical analysis, we can ignore it. Also notice uncertainties here. But just like we have a range, because ultimately also this line represents a mathematical relationship between our y value and our x value. And it's this direct relationship here that we have between y and x. And so as x increases, y decreases by some amount over time or over change in temperature. Just as there is uncertainty in each of these data points, there's also uncertainty in that mathematical relationship. And that mathematical relationship is related to the uncertainty of the data points. And to represent that uncertainty in our slope, we draw what are called max and min lines. And so, roughly speaking, we want to go from the top of our far left error bar, or our uppermost error bar, to the bottom of our bottommost, and from the bottom to the top. And those are terrible lines, and I apologize. Artist, I am not, and straight line drawer, I am not. Oh, maybe this will work. Border width, no, I don't know. Understand that those are supposed to be straight lines. Notice that the slope of this line here, though, is less than the slope of our fit line. This is what we call our minimum slope line. Notice that the slope of this one here is greater. This is our maximum slope. And that minimum and maximum slope represents the uncertainty in that mathematical relationship that's being described by the linear fit. And so in that way, we can now represent that uncertainty that we have because of our measurements. So it's kind of a cool thing. Now, we can only do it with linear fits, but, and we're going to skip over this because that's what we just talked about. But we can only do it with linear fits, which is part of why we get into this idea of linearization of data. And linearization of data, I'm going to have you go take a look at this link on your own. We're going to talk about it a little bit more in class because it is a little bit more complex analysis. But one of the reasons is because when we linearize data, we can get a better understanding of the uncertainty in that mathematical relationship if we put it in a linear model. Okay, that's it for this time. We'll see you in class. Make sure you come ready to ask questions. That's it.